All right, our next topic is to discuss how we can construct Poisson processes. So something that's important to understand is how do random variables get constructed? We might be able to specify a density, one that has the right properties, or at least one that integrates to one. But it's always a question of when does a variable, how does a random variable with that behavior come to fruition? Can we construct it? Can we make it happen? And the same thing's true of the Poisson process, where we had, for example, in potentially 2 dimensions or even 1 dimension, we have points scattered in a way that the number of points in non-overlapping intervals are independent Poisson random variables with specific intensity. Okay, let's think about this. So we're now trying to construct a scatter of points or a process on, we'll say, the unit interval. Okay, so let's let U1, U2, etc. be D uniform. Okay, so these random variables are going to fall all over the unit interval. U1, U2, U3, U4, etc. Now we don't necessarily care which ones fall where. We're going to define two count variables. Well, we're gonna define B1 as a subset, let's say, of the unit interval. So let's define B1 as, let's just say here. And then let's define B2 as everything else. So B2 is going to be everything else. So B2 is here, red. B1 is blue. Okay, and we're going to define N sub Bi for each of those two i's to be the number of the first capital N uniforms that fall within B sub I. Right, so this is the number of the first N UNs that happen to fall in B sub I. Okay. So let's define now X to be N sub B1, Y to be N sub B2. First question is, are X and Y independent? Okay. Something to think about is, are X and Y independent in this construction? Well, there's a couple ways we could show this. We could do this. One would be if we went to the definition. So X is a discrete random variable. X and Y are discrete random variables. We would need the probabilities to have these to be decomposed as a product. And we could try to work through the math to show whether it is or it isn't. But we can also reason about it and think, well, it's not possible. Why? Because once we know X, we know Y. Once we know Y, we know X. Right? So it can't possibly be Y right now. The number of points that falls in between in region B2 could be anything from 0 to 6. Right? If N is 6, capital N is 6. Could be anything from 0 to 6. But once you tell me that X is 3, I know that Y has to be 3 because the total is 6. So whatever the distribution was, it definitely didn't put 100% probability on 3, for example. So they're not independent. Okay. But now let's let N be a Poisson random variable. And let's make N independent of X and Y. Okay. So hold on. Let's let N be a Poisson random variable. And let's define little p to be the probability that any given uniform falls within B1. What is that probability? Well, B1 is a subset of the unit interval. And uniform random variables fall within subsets with probability the size of the subset, right? That's what uniform variables do. That's how they behave. And the probability that U is in B2 is just going to be 1 minus P, right? Which is the size of B2. All right. And now we're going to take, well, we're going to define X as the sum. Again, from 1 to N, but now the difference is that the upper limit of the sum N is a random variable in this case. So we haven't fixed it as a fixed integer, okay? So this would mean that if I tell you how many of the first random number of points fell within region B, does that actually tell me how many points fell in the other? No, it doesn't. It's still a random variable. Question is, what is this distribution, right? And Y is going to be the sum of the number of how many points fall within the first N, where N is Poisson in B2. Okay. Well, now how do we calculate the distribution, the joint distribution of X and Y? Well, we have random variables X and Y, and they depend on a random variable called N. And so when we have this, it's usually convenient. We usually want to work with law of total probability. So probability that X is equal to X, Y is equal to Y, given N is equal to little n, times the probability that N is equal to little n. Well, what do we know about this? Well, what we know is that for each N, I'm sorry. What we know is that for specific values of X and Y, right? So X, Y are going to be integers because they're counts. For specific values of X and Y, in order for x to be x and y to be little y, n has to be exactly x plus y, right? Because otherwise there has to be an extra point somewhere, right, to account to take them away from those values. Okay. Well, now what's the probability that x is equal to x and y is equal to y, given that n is equal to x plus y? Well, given the certain number of points, what is the distribution of where the points fall? Well, each point will fall within each region independently with probability P or Q. And we're just trying to count how many, in this case, successes, if we think of B1 as success and B2 as failure, we're thinking of how many successes. We want to have exactly X successes out of N. And so this is exactly a binomial random variable, right? With success probability P. And the distribution of N is Poisson. So this is lambda to the X plus Y e to the minus lambda over X plus Y factorial. So if we do a little work, let's get rid of this combinatorial coefficient and actually express it explicitly. This is just the binomial coefficient. And what we see is, well, when we look at this, we see that X plus Y factorial is going to cancel with X plus Y factorial in the numerator, or in the denominator there. We'll see that P to the X is can join up with an a lambda to the X. Q to the Y can join up with a lambda to the Y. And so what we can do is we can write this as P lambda to the X e to the minus P lambda over X factorial, noting that P lambda plus Q lambda equals lambda times Q lambda to the Y e to the minus Q lambda over Y factorial. So what does that tell us? Well, this is now a product of two functions. One function only depends on X. One function only depends on Y. So this tells us that X is independent of Y. X is Poisson. No. X is Poisson with rate lambda P. Y is Poisson with rate lambda Q. Okay. So then that tells us that that tells us this is how we can construct a Poisson process. So to construct a Poisson process on a closed interval, Poisson point process, and let's just do it on the unit interval with intensity lambda. We can do the following. Generate a Poisson random variable n with rate lambda, given the value of the variable, place points at uniform locations between 0 and 1. at n of the uniform locations. If we want to generate on all of the positive real numbers, so 0 to infinity, we repeat the above process independently for each for, let's say, the interval 1 to 2, the interval 2 to 3, etc. Conversely, if we have a Poisson process on with any intensity, on any region, given exactly n points in the process, the locations of the endpoints are independently can be represented or generated by u1 through un independent and uniform on that region. Okay, so those are two flip sides. Those are the flips, two sides of the same coin. To generate a Poisson, we generate first the number of points in a region, then we just lay down uniforms. Conversely, if we already have a Poisson, we can look in a region. If we know how, if we count how many, if we know how many occurrences there were, then conditionally on the number of occurrences in a given region, the distribution of points is uniform. So that's a concrete construction of the Poisson point process, which again boils down to the uniform distribution at some point in the process.